Okay, so now we look at radioactivity. Radioactivity discovered by the great Marie Curie, and what we focus on in radioactivity are three main types of radiation. The three main types of radiation that we focus on would be alpha, beta, and gamma. Right? What are alpha particles? Alpha symbol here. Alpha particle is simply a helium atom we looked at before. Beta particle is what we know as an electron, right? Basically zero mass, -1 atomic number, and a charge of -1. Gamma is basically energy, right? It's not a particle, it's just energy. Right, so if we look at the alpha and the beta particle and the gamma, we notice that the alpha particle is a bit larger or a bit heavier than the beta particle, and gamma is just a ray, so it's not a particle at all. It's just a substance of energy, right? And about the alpha, beta, and gamma, the alpha particle is stopped by a sheet of paper. So if we have an alpha particle and a sheet of paper is placed in front, the alpha particle will not be able to penetrate the sheet of paper. Beta is stopped by aluminum, and gamma, which is the most penetrative, can be stopped by a few centimeters of lead. How far will they travel in air if there is nothing to stop them? Alpha will travel a few centimeters, beta will travel a few meters, and gamma will travel a few kilometers. Right? These particles now, suppose these particles were exposed to an electric field or a magnetic field. How will these particles behave? Well, a beta particle is a negatively charged particle. Alpha particle is a positively charged particle. So think about it. When we have like charges attract, unlike charges repel. So where do you think a beta particle will travel? A beta particle is negative. So a negative should be attracted to the, very good, positive. So the beta particle will travel and be attracted towards the positive. Alpha now, alpha is positive, so it should be attracted to the negative. Very good. And will it travel the same distance or will it go further? Very good, it will go further. Why? Because the alpha particle is heavier. So the alpha particle will travel a little bit further before it's pulled in by the electric field. What about gamma? Gamma has no charge. So if something that's not charged is traveling through an electric plate like that, what will happen? Well, nothing will happen. The gamma particle goes straight through. It's undeviated. Right? Magnetic field now. So electric, magnetic field. What will happen in a magnetic field? Let's start with gamma. Gamma, neutral, goes straight through again. Very good if you guess that. Alpha particle. An alpha particle is a positive charge. Try to remember. When we looked at Fleming's left-hand rule, what we said? Fleming's left-hand rule showed that in the presence of a magnetic field, a current carrying conductor will experience a force. So, same thing applies here. A current carrying conductor, conventional that is basically a positively moving particle. So, if I have a positive moving particle in a magnetic field, it should experience a force. So, let's see if we can work out the direction of the force. So these two particles will experience a force. Let's see if we can work out the direction. Remember, Fleming's left-hand rule is for direction. It gives you the direction. So, magnetic field cross means inwards. So the magnetic field is inwards. This is current direction, and the current direction is conventional. So it shows the direction of a positive charge, which is positive. So this particle is moving in this direction. So what will happen to it? It will move upwards. Magnetic field inwards, direction of current, which is the positively charged, and the direction of the force. So it will travel and go outwards. We can do the same thing for the electron, but a good guess would be what? Opposite direction, shorter distance. Let's see if it works out. Magnetic field is this way. Beta is negative, so that's reverse of conventional. So that's not this direction. It's the opposite direction. So although the beta is going this way, current direction would have been opposite direction. Conventional flow is positive charge, right? This is beta. Beta is going this way, so a positive charge will be going in the opposite direction. So therefore, it will go downwards. Follow that? So that's the behavior of alpha, beta, and gamma in a magnetic field, alpha, beta, and gamma in an electric field, what it's stopped by, and range in air. Okay? We need to also look at what will in a equation. So let's say a particle. Let's just make up a particle, right? Let's make up a particle. Let's make up a Madrid particle. It's a Madrid particle, ME. Let's say it says 23192. Let's say this Madrid particle, right, loses an alpha particle. What will happen? If it loses an alpha particle, then an alpha particle is taken out of this. So an alpha particle is what? 4,2He. So if I take 4 out of here, what will I get? 231 minus 4. If I take 2 out of here, I will get 92 minus 2. And let's call the particle, this is Madrid, I call this real, right? So if I take 231, if I take 4 out, I will end up with this. 231 minus 4 is 227, 92 minus 2 is 90, Re. So if it loses an alpha particle, one alpha particle, this is what will happen. So what does this mean? Basically, this is balancing equations. If I add up the nuclear numbers, 227 plus 4, I must get this. And if I add up the atomic numbers, 90 plus 2, I must get this. Fair enough? Let's say now this Madrid particle lost a beta particle. What will happen? Beta particle is what? A beta particle is simply an electron. So, based on the last example, we should see that the mass number shouldn't change. So that will be 231. Right? That's the same particle, Re. Right? I use R. Let's use R. And what will happen now? This plus this must be equal to 92. So this value here is what? Very good. It's 92 minus 1, which is 231.93. Let's check it again. 231 plus 0 is very good. 93 plus minus 1 is 92. So that's the way you balance these equations if based on the particles that you lose. Let's make sure the reactants and the products, the nuclear and the atomic number adds up to be the same. Okay? And what will happen if you use a gamma particle? Oh, not gamma particle, gamma ray. Just making sure you're on the same page with me there. Right? Gamma. Well, gamma is just energy. So the atomic number and the nuclear number shouldn't change. So what changes? All changes that the particle loses energy. And that's it. Alright? So that's what you need to know about the first part of radioactivity. Okay?